Antiderivative, we've talked about concavity, points of inflection, critical points, cusp points, all that vocabulary has come on. And so what I wanted to do is redo this video as sort of a second pass at the derivative as a function, and let's just see where this takes us. So the same introductory problem as before. I have a function, g, which is a degree 4 polynomial. That's not so important right now. But what we're going to do is we're going to generate the graph of g prime. And what I mean by that is we're going to look at the derivative at different places. So if I picked this point over here and I drew in a tangent line, what I know is that the slope of the tangent line over there is positive. So when I come down to generate the graph of g prime, for that same x value, I expect that the derivative is going to be positive above the x-axis. Now, how far above the x-axis? We can't really determine that yet. And so if I pick another point along the curve, that tangent line is steeper, so it's still positive, but it'll be more positive. So I expect that that point will be up there. Well, let's go for some easy points. Right over here where I have a relative maximum, the slope of the tangent line will be equal to 0. So if I drop down, my derivative will pass through that point. Over here I have a relative minimum. Slope of the tangent line is equal to 0 there as well. So when I go down to the derivative, I expect to have a root. Slope of the tangent line over here at the relative minimum, also equal to 0. We could play this game for every single point along the curve and generate the graph of the derivative down here. Or we could be clever and we could look at the behavior of this function. So if I look at g, what I see is for this part of the function is decreasing. Well, if g is decreasing, then any tangent line I draw to the function along this part will be negative. So when I go down to the derivative, I expect my derivative is negative until I reach the x-coordinate for the relative minimum. So let me do that one more time. When the function is decreasing, the derivative will be negative. The derivative is going to be below the x-axis. The function is decreasing until I reach this relative minimum. That means the function is going to be negative until I reach the root of the derivative. And I expect my function to look something like that. After I reach the minimum, my original function increases until I hit the max. Where the function is increasing, the derivative will be positive, and so it's going to do something like that. Let's go back up to the function. We're decreasing from the relative max to the relative min. If the function is decreasing, your derivative is negative. And after the relative min, continuing on forever, that function is increasing, so the derivative is going to be positive. And this will be the graph of g prime. Now, what we've done since last week is we've actually gone even further. We not only will take the derivative of a function to generate its graph, but we could take now the derivative of this function and generate its graph. I would say I have a relative maximum over here, so the slope of the tangent line will be equal to 0. I have a relative minimum over here, so the slope of the tangent line is 0. Where the blue graph is increasing, the slope of the tangent line will be positive. It's increasing over here as well. The derivative is decreasing, so the slope of the tangent line will be negative over here. We can take this information to make a new graph. From there, we could do it again. We could find the first derivative. We could create a graph of a second derivative, a third derivative, and so on. So, in addition to taking the derivative of a function, like we just did, we can take the derivative of a derivative, which is what we're going to call the second derivative. We would even take a derivative of the second derivative, and we would call that the third derivative, but we're not going to spend a lot of time in the third derivative. It doesn't give us information about the graph that we're interested in. We could even go backwards, and we could find the antiderivative. And the visual that I like to have is this. If f of x represents my original function, okay, if f is my original function, when I take a derivative, that brings me down to f prime. That is a graph where I look at the slope of the tangent line for every point along this curve. Well, I could take another derivative. That's what we call f double prime. F double prime is the derivative of the original function. I could find f triple prime. I could find f quadruple prime. You can take as many derivatives as you want, but you can also find something called the antiderivative. The antiderivative is basically reversing the derivative process. This big F, if you were to take its derivative, will give you the original function. And right now, that's just an idea that I'm trying to get out there with my kids. Big F is the antiderivative of little f, meaning if I had big F in front of me and I took its derivative, I would get this original function. And we're going to continue playing with that over the course of the next several weeks. So, all right, so what we have now is we have the graph of a function, and your job is to find which of these four curves down here will be the derivative of this function, and then which one will be the derivative of the derivative, so the second derivative, and which one is the antiderivative. So let's go through that process together. What I know is that my function over here has a relative minimum right here, so f prime is going to be equal to 0. I know that my function is decreasing before I hit the relative min, so f prime is negative. And I know that my function is increasing, so when I look at the derivative, I expect the derivative to be positive. So, of these four functions, I'm looking for the one that changes from being negative to being equal to 0 to being positive, and the change happens somewhere between 1 and 2. Well, that's not the behavior over here. That does seem to be the behavior of this line down here. I'm somewhere between 1 and 2 when my derivative has a root. Before that root, my function is negative. It's below the x-axis. After that root, my function is positive. It's above the x-axis. This actually has the desired behavior. That one is f prime. Now, if I want to talk about f double prime, there's two ways we could go about doing this. We could look at the concavity of this graph. My original graph is concave up. It is a cup that will hold water. And what we know is that when a function is concave up, the second derivative is positive. So we could have that conversation. Well, this function is concave up everywhere, so I need the second derivative will be greater than 0 everywhere. Not this one. This one has points below the x-axis and above. This one over here has points below the x-axis and above. It's only this one over here, that horizontal line, that is always above the x-axis. It's always positive, so that is the graph of f double prime. I said that was one way we could go about doing that. Our other option would be to look at the derivative, the original derivative, and find its derivative. Well, if I find the slope of the tangent line over here, we're going to find f prime prime is going to have to be some positive number. How do I know it's a positive number? This line is increasing. Well, if it's a line, then the slope of any tangent line is going to be the same. It'll always be the same positive number for any point along that curve, which is further evidence that this is the graph of f double prime. So make the determination based on concavity or make the determination based on how the first derivative is behaving. Either way, this is f double prime. Now we need to figure out f, big F, the antiderivative. Well, if for the antiderivative, big F, what's so special is that when you take its derivative, you get back your original function. Well, let's look at the graphs here. If this is the antiderivative, well, I see that the function is increasing until I get to 0. Well, what does that mean? That would mean that the derivative of this function has to be positive along there, and that it has to be equal to 0. Since this function is decreasing, I would expect the derivative to be less than 0. It's going to be equal to 0 at this minimum point, and then after that, it's going to be positive. So I'm looking for, if this is truly the derivative, I need for the function to go from being positive to being equal to 0, to being negative, to being equal to 0, to being positive. Look at what happens. This function is positive because it's above the x-axis. It's equal to 0. Then it becomes negative. It then becomes 0. And then it increases. This is what we call big F. That's the antiderivative. This guy over here doesn't have the correct behavior, so that's my distractor. Okay, let's try another one.